All right, welcome back. So this is going to be the second and final video in our equation series for the final exam. Now remember I said in the last video I am not going to include the torque and angular momentum portion because I already made videos on that. So I would suggest going to look at those videos in order to remember what those equations are. I'll also include that link when I post this video. So now let's talk about fluid dynamics. This is something that we didn't test on the last test, and so it's very important that you understand it for the final. There are two primary equations that we talk about when we talk about fluid dynamics. The first one I want to talk about is actually the second one I have written here. This is that A1 times V1 is equal to A2 times V2. Now, this is what's called the continuity equation. For fluids. And what it says is that the volume per second that flows through a pipe is constant. You can change what the area is, and that's in turn going to change what the velocity of the fluid is. So if we consider some pipe like this that has some area, and there's going to be some velocity of the fluid here, so let's call this A1 and V1, and this pipe changes its thickness, then if this is the area A2, there's going to be some velocity V2, okay? So this equation tells you how to deal with fluids in a pipe when the area changes, and how does the velocity change as a result of changing the area. Now, the first equation that I have written here is what's called Bernoulli's equation. Bernoulli's equation. I think he's Italian. I don't know how to spell Italian names. I think this is the way that you spell it. So what Bernoulli's equation allows you to do is it allows you to find what the pressure and the velocity and the height are for fluids. That's not a very good explanation of Bernoulli's equation at all. What Bernoulli's equation does is it relates the pressure in a pipe to the speed of the pipe and the height that the pipe is at. So if I consider some system where I have a pipe that is going to go up to some height like this, and I have, so here's our pipe. This has some velocity V1, this is at some height H1, and there's some pressure P1 here. This is going to have some height H2, some velocity V2, and some pressure P2. Okay? So if we know what these quantities are, what we can do is we can combine them in Bernoulli's equation to say that this forms some constant. And that allows us to find, for instance, if I know what the pressure, the velocity, and the height is at the bottom, and I want to find what the pressure is at the top, and I know what the velocity and the height is, I can calculate that. Now, by combining Bernoulli's equation and the continuity equation, we can actually do problems where these areas, so this area at the bottom and this area at the top, are going to change size. It gives us a system of equations that we can solve. The next important equation that we need to discuss is the linear expansion equation for a metal if you increase its temperature. And so let's say that we have some metal bar here, and it's at some temperature we'll call Ti, and it has an initial length of L0. We want to see how much larger this bar gets. So this is going to be the same length, L0. This is going to be some change in length if we increase this temperature to some Tf. So this equation says that the change in length is going to be equal to alpha, the expansion coefficient, times the initial length times the change in temperature. Now this quantity here, alpha, is going to be different depending on what material it is. So if I have a steel rod versus a copper rod or an acrylic rod, those all have different expansion coefficients. All right, so chapter 18 is all about thermodynamic processes. So to start out with, we have the ideal gas law. The ideal gas law can be written in two forms. This form, which is in terms of the number of moles and the universal gas constant. So the number of moles is lowercase n, and the universal gas constant is R. Or it can also be written in this form, which is in terms of the number of particles, which is capital N, and the Boltzmann constant, which is K. Okay. So what the ideal gas law says, let's say in terms of the number of moles, is the product of the pressure and the volume of a gas is equal to the number of moles times the universal gas constant times its temperature. So this is a really useful equation, and we'll see how that comes into play when we talk about these thermal processes. Another really important equation is the equation for the internal energy of a gas. And so the internal energy of the gas is U is equal to 3/2 times N times R times T. The last important equation that we have in this little subsection I have is this equation. This equation is the first law of thermodynamics. It says that the change in internal energy is equal to the heat added to the system minus the work done by the system. And so if you look at the units of the first law of thermodynamics, it's actually the same as conservation of energy. So you might think, and you would be thinking correctly, that the first law of thermodynamics actually comes from conservation of energy. So now let's talk about specific thermal processes. So there's 4 thermal processes that we talk about. The first is what's called an isobaric process. So baric is, I believe it comes from Latin. It's the same word or the same root that we have for barometer, and that means pressure. And so at constant pressure, if we draw the line for our PV diagram, that's going to look like this. Right? It's just a horizontal line. So that corresponds to the isobaric process. Now, the isochoric or the isovolumetric process is a process where the volume is constant. That is going to look like this. Okay? So that's our isochoric process. Now, we have 2 more processes, the isothermal and the adiabatic process. The isothermal process is a process where the temperature is constant. And so that's going to look like this. Okay, so that's our isothermal. And the last one is the adiabatic. So the adiabatic looks a lot like the isothermal process, only decays much faster. Okay. All right, so those are our 4 processes. And so what I have here is a table that will allow you to calculate the work, the change in internal energy, and the heat for all 4 of these processes. So for instance, if I wanted to find what the work was for the isobaric process, I would just go to this part of the table here. There's my work, and that corresponds to this one, right? Because I have the red and the red. Same thing for any one of these. So if I wanted to find what the change in internal energy was for the isothermal process, I would look at this part. Because this is the isothermal portion, and that's the change in internal energy. Now, what makes an isothermal process an isothermal process is the fact that the change in internal energy is 0. Because remember, the internal energy is going to be equal to 3/2 nRT, and so delta U is going to be 3/2 nR times delta T. And for isothermal, that means that the temperature is constant, so the change in temperature is 0. So the change in internal energy is 0. The adiabatic process is, the thing that's special about the adiabatic process is that the heat added or removed from the system is 0. Okay, so I hope these videos have been helpful, and I wish you guys the best of luck on your exams.